First, I would like to thank the organizers for inviting me here and organize such a wonderful conference. So I will start with the Fine-time approximation. Well, I only talk about the Fine-time approximation in the two-dimensional Euclidean space. So let me introduce a metric, some notation actually. So for a pair of real numbers, we have this to be the distance to integers. That means it's infimum of PQ in Z and the maximum of the distance between alpha and P and Q. So let me remind you of Dirichlet theorem. Probably everyone knows. So for any alphabet, real numbers, and real number Q bigger than 1, there exists little q less than Q, such that the distance of Q alpha and Q beta to the integers is less than or equal to 1 over Q. That's the Dirichlet theorem. And we say that Dirichlet theorem is improvable for alpha beta if there exists sigma bigger than 0 less than 1, such that and Q0 bigger than 1, such that for Q bigger than or equal to Q0, there exists little q, which is slightly better than this. That means smaller than Q sigma times Q. But the approximation is slightly better. That means that the distance to integers.
Should that be square root of Q? Yeah. In Dirichet's theorem?
Oh, yes.
Square root of Q.
Yes, I think you're right. Maybe I should put the Q squared here, I think.
Square root.
No, squared. Or the Q squared here, I think. Then Q squared here also. And then less than or equal to sigma divided by Q. That means we use smaller integers to have better definite approximations. Well, it's well known that the Dirichlet theorem is sharp. That means for almost every alphabet with respect to the big measure, Dirichlet's theorem is non-improvable. And the result of Nimish Shah said that the similar phenomena holds for all curves. So let's see the curve. I assume that it's analytic, non-planar. Then for almost every S with respect to the big measure, Dirichlet's theorem is non-improvable. For EX. Well, I mean, let me give a remark here. It's reported by Nimish that analytic can be replaced by a weaker assumption. By non-degenerate, by differentiable non-degenerate. Well, non-degenerate is kind of non-planar assumption for the differentiable curves. And this is also Nimish. And it's also told me by Anzidler, by private communication, that he has another proof of this. So after this, what's left? I mean, the question left. It's the straight lines. And fractals. That's the subject I'm going to talk about today. So the main theorem is the first one deals with straight lines. So is that big enough? I think it is. I think it is. Okay. So let AB be two real numbers, and assume the following condition holds. We'll call it star, and it will be used later. Assume that there exists epsilon bigger 0. There should be this will be a Diophantine condition for A, actually, such that the infimum of Q in natural numbers of Q 2 minus epsilon times the distance of QA to 0, to integers, is positive. Then the conclusion is for almost every S in real numbers, Dirichlet theorem is non-improvable for AS plus B and S. This is the straight line. So let me give some remarks to interpret this result.
So A and B such that, no, B there's no condition.
There's no condition for B.
Okay.
Yes, that's just A. So let me give a couple of remarks to interpret this result. First is, well, when we give a condition, we would like to know the exceptional side.
A and B are in R.
Yes, yes. Thank you. And first remark is the following. Well, the real numbers with star not whole. This set has Hausdorff dimension 2/3. Hausdorff. And well, this is 2. 2 is very good. 2 is bigger than 1. So in particular, for A equals square root of 2, this theorem holds. I mean, square root 2 means it's badly approximable real numbers. 2. So why do we need this condition? I mean, what are we using? Star is only used for non-escapable mass. Star is only used for non-escapable mass. Let me explain this. So suppose I'm going to explain what non-escapable mass means. So suppose lambda is a probability measure on R2. Well, here should be the volume measure of a segment. And then we can map R2 to S3R, where alpha maps to this one, which we will denote by U alpha. We will see later that the Dirichlet improvement is closely related to a diagonal. It's closely related to a diagonal flow, GT, which is e to the t, e to the t, e to the minus 2t. And for each, and we can further max it to S3R over S3Z. And we will denote that. Just the alphabet to the element in the quotient space, I will use a bracket. Therefore, a probability measure here will define a probability measure here, which I will denote by lambda tilde. So 9. So non-escapable mass means so non-escapable mass means that for any big star limit of the following measure of 1 over t, c, then the push forward of lambda tilde by gt as capital T tends to infinity is a probability measure.
For number remark 1, I think the dimension of this set is 1, right? It's not 2/3. It's
because there is this extra cube, right? Instead of 2, you put 1.
oh, I
No,
see.
it's one dimensional. It's real number, not two dimensional.
I see. So this is just the Jarnik-Besikov theorem. That you
Yes. You told me. And
I see.
okay, the first result about straight lines.
So is it optimal? Say if you don't have this condition, do you actually get escape?
No, actually, it's very strong. I mean, no, it's
So it's stronger.
yes. I mean, we can supposedly theoretically we can make it easier. No, sorry. Theoretically, we can make it. Sorry. I always forget to do that. It's not early. It's a joint work with Berkeley. Sorry about that. I mean, you will see variety views. I mean, it's a very strong assumption for non-escapable mass. Okay, the first one, the second one. This should be good. So the next result is about fractals. Well, you will see that, I mean, the only obstruction for our results is non-escapable mass. So non-escapable mass is very important for us. But unfortunately, we cannot do it for very generalities. So second one. That's my old result. gamma be a hyperbolic matrix. Hyperbolic. And lambda be a probability measure on unit cubed, which we'll consider measurably as T2. Therefore, gamma gamma acts on it. Assume lambda is gamma invariant and ergodic, and has positive entropy. That's one assumption. Two. The two should be. I need to figure out the statement. Oh, lambda does not have full escape mass. It's different from the previous one. Previous one is stronger, but this is weaker. Does not have full escape mass. That means the limit does not converge to 0. T GT lambda tilde. The push forward of lambda tilde at above does not converge to 0 as capital T and infinity. On these two assumptions, we have the same conclusion. Then, for lambda almost every vector v, we have that Dirichlet theorem is non-improvable for v. Then what here? Okay. Now we're going to discuss some proofs. Our proof will be were homogeneous dynamics. So, okay, that's notation. Let me use this. Maybe theorem A also. No, I'll keep it actually. Maybe I've only keep the conditions. Actually. So the proof, now let me discuss some links between the Fine approximation and homogeneous dynamics. This is due to actually Dani. So the homogeneous setting, the notation will be as above. Then you can see that means with X and this map and GT. We need to define a height function from X to actually starting from 1 to infinity. So first X can be identified with unimodular lattice in R3. That means for G, it corresponds to GZ3 cubed. The height function will be defined by the supernorm of the shortest non-zero vector. super norm. Sorry, it should be the inverse actually. Sorry about that. It should be super super. Vector V belongs to the lattice corresponds to G, but then 0, and then we take the super norm. That means it's the maximum of the component in absolute value. Let me take inverse. In that case, our space looks like, rough speaking, like this. Let me draw it. Okay. Then there's a function, height. That should be strictly touch the bottom. Then we have height here. And for each sigma, we define the compact subset, K sigma, to be those lattices with height strictly less than or equal to sigma inverse. No, yeah, sigma inverse. It's, this subset will denote by K sigma. So by words, K sigma with sigma bigger than 0 less than 1 should be the lattices in X with height X less than or equal to sigma inverse. And the usual correspondence said the following. So alpha beta is Dirichlet improvable. That means Dirichlet theorem can be improved for alpha and beta if and only if the trajectory, I think it's something here. Say something here so that you can see. The trajectory under the diagonal flow eventually leaves some of the compact subset. Let me write it down. If and only if there's this sigma bigger than 0 less than 1, such that and T0 bigger than 0, such that the trajectory from capital T0 T, then if U are beta for T bigger than or equal to T0, this trajectory intersects K sigma is equal to empty set. Let me keep this. So conclusion is the following. That's the one always used in the dynamical approach for the Dirichlet non-improbability conditions. So the conclusion is currently is following. I will call it conclusion. If the trajectory is dense, if the set gt u alpha beta is dense, then Dirichlet theorem is non-improvable. For the vector alpha beta. Okay, that's the link, and now I'm going to talk about the proof. Now I'm going to talk about dynamical results that will be obviously imply this, and then the theorems A and B actually. The third part will be homogeneous dynamics.
Could you repeat what is K sigma? K sigma is the compact factor.
Yes. Yes.
Say it again?
And you want the intersection to be empty or not empty?
Improbable means empty. For some sigma, probably very close to 1. And then there's small part it must
So
miss
it's outside of
eventually.
So how sensitive is this notion of derivative improbable to the suit norm? Is it just the if you changed it to some other norm, is it just the bound on sigma that changes? You see, sigma is between 0 and 1, but that's really special. The upper bound on sigma.
I think all he's trying to prove is that it's dense in this. Almost all. Yes. That's the main point.
Yes.
Dynamically. That this is dense.
Okay, that's all.
Sigma 0, well, that's because the bottom, I mean, the
Yeah, it just changes the bottom.
lowest height is 1, so.
Right. But if you didn't use the suit norm,
Mhm.
the bottom wouldn't be sigma. It's 1.
Then it's not very clearly how it relates to the Dirichlet theorem because it's other norms. I mean, you can define the height, but not very clear to me how to relate to the Dirichlet theorem actually. But maybe it's the same dynamics. Oh. So one theorem we're using for both of the theorem A and B is the measure classification theorem due to Dirichlet cutoff and Lindenstrauss. So let me write it down. That's due to Dirichlet cutoff and Lindenstrauss. So let mu be a probability measure on the space. And suppose that mu is invariant under some Cartan subgroup. I just split Cartan. Cartan subgroup, which we denoted by A. We don't need the full strength of this theorem. No, actually, we need. That's one assumption. 2. It's invariant and algorithm. And algorithm. We obviously need that. The second assumption is mu has positive entropy for some element in A. Positive entropy for some. Then the conclusion is that the only possibility for mu is the probability parameter, X. Now we turn to the proof of theorem A about straight lines. Next result, well, it's just some observations, but let me have a theorem. There are not many here. The main result, okay. Now it's a proof of theorem A about straight lines. The main dynamical result is the following. Due to me and the Bragg-Weiss. What did I say? So let mu be a always probability measure on X. And let F be a one parameter diagonal group. Diagonal means diagonal over R. One parameter diagonal in SR3R. And U be a one parameter unipotent in the group. The two main assumptions. Assume the first one, U is normalized by F. And FU is non-abelian. The second one is about the diagonal group. We assume that F has no non-zero invariant vector. F has no non-zero invariant vectors in R3, where the natural action. The conclusion is that then the probability Haar measure is the only FU invariant probability measure on the homogeneous space. On X. I will come back to the proof and the explanations for the assumptions later, but let me now to use this result give a proof of theorem A about straight lines, and also the extension, also the how to remove the analytic assumption in Shah's theorem. So basically, this theorem says following. So the unipotent invariance plus negative mice implies equidistribution.
So this is somehow reminiscent of this result about epimorphic groups. So I guess in your case, there could be some groups of U which are not epimorphic.
Yes, yes. In the most of the cases, non-epimorphic. Yeah. Let me maybe give my example. No, it's actually never epimorphic. Sorry, it's never epimorphic, I would say. Any example is never. So the example is our case, e to the t, e to the t, e to the minus 2t. That will be corresponds to F. And U is given by this type of matrix. It's not epimorphic. Okay, so basically, theorem C says following. Unipotent invariance plus negative mice of mice for the implied equity distribution. For the following type of things. GT lambda tilde GT. Here's our GT. Lambda tilde is the one associated to some measure on R2. So there are two applications. What we have. First one is analytic curves. For curves.
I'm confused about the condition B.
Oh, okay. Condition B said that this is allowed, but et e minus this is not allowed.
It says it has, oh, it's a non-invariant. I see. Not invariant.
Okay.
I see, okay.
Curves. So unipolar invariance is given by a trick of Nimish. Okay, Shah's trick is 2009 paper for implied unipolar invariance by twist. Next minus is given by Kleinbach-Margulis. It's given by Kleinbach-Margulis. Year is maybe 96? No, 98. So for curves we have equity distribution, and then equity distribution implies that almost every point the trajectory is dense. That means implies number theory without not a straight line. In Theorem A, unipolar invariance is free because it's a straight line. Net cube mass is due to, actually I need more space, so put it like that. Oh, I still have star, yes. Net cube mass is given by the Dirichlet and Villani. They're not here yet.
They're probably watching from York. It's translated.
Oh, yeah. Dirichlet and Villani in 2011. They proved following. They proved roughly speaking, for A satisfies the star, the straight line as plus B contains a badly approximable vector. That means the trajectory of this vector in harmonic space on this flow is bounded. Then we can use Dani-Margulis, said that unipolar trajectory never escape mass. So we can use Dani-Margulis. Also Dani-Margulis in 93 maybe. Then we have this. We see that this this condition is very strong for next mass. Of course, potentially we can weaken it, but we don't know how to do it right now. And I would say that this condition, we can have better, there's no condition here for B, but we can also put a condition for B. And it's in the ongoing work of Jinpeng An and Villani. I think Jinpeng will talk about it later. Okay, I'm done for this case actually. It means that for any complex subset, a unipotent trajectory from complex subset, most of them will be in another compact subset K prime.
So
But-
you're using the same thing for curves as well, right? Kappa Margolis result is just the.
Kappa Margolis for it's for curves.
Right.
I mean, this for uniform trajectory. No, sorry. That uniform trajectory. Let me see.
So I didn't understand. So how do you conclude the non-escapable mass?
How do I conclude that? Can I make the mistake? Hopefully not. Okay, so there is a point that in a compact subset, and then it's curved. So it's like uniform trajectory. Sorry. It's let me do it here. So it's so it's SAS. It's 1, SAS. I mean, the straight line in this trajectory of let's say some point x0 by 0. It's unipolar trajectory. The line is unipolar trajectory of this point in homogeneous space. And the badly approximable means that this trajectory stays in a compact subset. Therefore, the unipolar trajectory, I mean, only has nice group mass. Does it make sense? No?
I understand.
Oh. Okay.
It's her question.
No.
The Margolis theorem says that if you have a compact set in epsilon, you have a larger compact set, you take any uniform trajectory, any piece.
Okay.
At least
Read
once
that?
somewhere, the first compact set, 1 minus epsilon proportion remains in the bigger compact set.
And you're saying, and this
So
line
because of
is a
DA,
uniform
because of DA condition, at least one point.
Okay, now it's clear. Yes.
The other thing he said,
Yes, that is it.
explain about Dirichlet's condition, that it satisfies some Dirichlet's condition with small thing, then it should remain outside a compact set. But since because of this condition, it may enter the compact set at least once. That's why. Just saying that because there is at least one BA point, it must enter a fixed compact set. That's why.
But it stays in a compact part for a long time.
1 minus epsilon proportion. Because of that,
Because
another
of
big,
that.
larger compact set.
Okay, now let me talk about the proof of C. Before talk about proofs of theorem B. That's what I mean C. So basically, in theorem C, we're going to talk about the classification of measures invariant unsolvable groups. It's about classification of invariant measures, I would say on X, for solvable groups. Well, the example is FU. This is studied earlier by Shahamoses, 95, and Margolis Tomanov, and by Margolis Tomanov, 96. For general homogeneous space. So there is structure theorem. Basically, the conclusion is following. The fact, due to these two papers, let me just state facts using this concrete example. Actually, it's the same. There exists a connected subgroup H of SS3 such that all the ergodic components for the group U is an H orbit. Is an H orbit. And we have very strong restriction to this H. First, H is normalized by F. And another one, the other one is very restrictive. The normalization by F preserves the higher measure. And normalization preserves higher measure. So therefore, there's really not many choices of H in view of the measure classification of Dirichlet and Lindenstrauss. Let me only talk about the dangerous case, the only dangerous case. Maybe dangerous. I think I can use that. No, probably I need that. I will use that. So the dangerous case. Actually, GT is the same, but let me make a change of variables and a change of basis so that the group H looks better. So let AT equals e to the t minus 2t and e to the t. And U is as before. Oh yeah. And U is given by this. And then H could be the following: the upper triangular matrix. See that whether, AT can parameterize the homogeneous measure for H. The observation to handle this actually simple, because this H is a unipolar radical of minimal parabolic subgroup. Therefore, this is measure mu. You mean what about which measure?
H normalization preserves higher measure.
The normalization of F preserves the higher measure of H. Higher measure of H. That's the restriction of H.
Yeah.
Here it preserves normalization of AT because that's opposite and this is 0 actually. This is 3t minus 3t is 0. So the observation is that for any periodic, maybe homogeneous H orbit, say HG, we have the following. The AT trajectory when V goes to 0, infinity actually goes to the constant. Here we use that any two Q-rational parabolic subgroup conjugated by some rational matrix, and then we have this. Okay, that's basically the only dangerous case. And I think I should discuss the conditions, whether they're important or not. Well, the second one, where is it? Where is C? Are you ready, C? Okay, then I will not discuss conditions, only mention one. For the if that's true, whether in higher rank it's true. For this, theorem C is not true. There are counterexamples because as the measure classification, the homogeneous measure emerge under this type of things. And diagonal, I would say A. But we don't have counterexamples for primes. So for say for P. For replaced by P is prime. And the expectation, possibly true, is that any even measure is homogeneous, but we don't know how to prove it yet. There's no such simple algebraic argument actually. Okay, so now I'm going to talk about the B. Prove theorem B. Theorem B actually is just some entropy estimate. So idea for the proof of theorem B.
Sorry, what did you say again? What was theorem B? Just remind us.
Okay, theorem B is that there is a hyperbolic matrix. Yeah, that's a good question, so I should do that. And the lambda in the T2 is gamma invariant and ergodic and the positive entropy. And no full mass loss under diagonal flow. That is the assumption. And for this gamma, we associate it to a hyperbolic matrix in SS3R, the G gamma equal to gamma 0, 0, 1. And GT as before. Theorem B said that lambda almost every point is Dirichlet non-improbable. Basically, we're going to prove the actual distribution. Actually, yeah. Let me just say that. The fact that the dynamic effect under these two assumptions, we will prove the following. There exists sequence Tn and infinity such that the sequence, the average, the limit of the average, lambda tilde just put that in the homogeneous space, put lambda in the homogeneous space. Convert it to some C mu x for some C bigger than 0. That's the main dynamical result used to prove theorem B. The question is how to prove this fact. I'm not going to prove this because this is more involved in calculations. But I will talk about the main ingredient or the key proposition. Suppose there is some limit. If there's another color. Suppose this is equal to nil, and nil is not equal to 0. Then we do a ergodic decomposition. Ergodic decomposition with respect to the GT and G gamma commutes with respect to the group generated by GT and G gamma. Therefore, nu is equal to same space X, nu X, d nu X, where nu X is the ergodic probability measure with respect to this. So the key proposition would be the following. Proposition for almost every X, the probability measure has a positive entropy. Then the positive entropy of this with respect to this gamma is preserved as a positive entropy with respect to the gamma. Then roughly speaking, this is almost the two-dimensional Cartan, and then we can apply that theorem. Finally, I would like to discuss the condition, which is to me is the only abstraction of no full escape mass. Let me call it maybe star. Star holds if lambda is friendly, or maybe let me say this, yeah, friendly. Friendly is the condition defined by Kleinbach, Bergweiss, and Lindenstrauss, and lambda is basically fractals, nice fractals, friendly something, or the Hausdorff dimension of lambda is big. I would say this is given by Kleinbach, Lindenstrauss, and Bergweiss. Or the Hausdorff dimension of lambda is bigger than 4/3. Well, 4/3 is the Hausdorff dimension of singular vectors, proved by Eva Cheng. So that's a reasonable assumption. This is due to Ziegler and Kitty-Rao. This one, Hausdorff dimension, bigger than 4/3.
You mean that the divergence on average is at most 4/3 is
Yes.
So that this condition.
Yes. Then we have some mass left. Okay, I think I will stop here. Thank you very much.
Clarify just this condition.
So
where does Eva Cheng come in picture? Which word? Einzitler.
Well, Einzitler and kind of improved my result, showing that the dimension is of divergent on average, not just diverging, is 4/3. So the bigger set of the divergent on average trajectories is dimension 4/3.
If lambda has Hausdorff dimension bigger than 4/3, then there's no full mass left. That means for some sequence Tn, the limit is actually for them is any limit is non-zero. And then Eva Cheng proved that the singular vectors has Hausdorff dimension 4/3. That means the vector that on the diagonal trajectory tends to infinity. No, sorry, it leaves compact subset eventually. That singular vector has Hausdorff dimension 4/3. Okay, I'll stop here. Thank you.
So what was the result about, you said there were two results, lines and fractals. So what was the fractal result?
That's the fractal result.
Theorem B.
That's a fractal. The positive entropy, so it's fractal. And if not full entropy, so then it's fractal.
So Dirichlet improvement for friendly measures, is that? So what is the statement of Dirichlet improvement for fractal?
Okay, given the probability measure, use gamma invariant ergodic positive entropy, we can construct this by symbolic dynamics, and then for lambda almost every point, Dirichlet theorem is non-improvable. This lambda is fractal, to me, because now the Hausdorff dimension is not full.
almost every derivative of your curve is satisfies that condition epsilon.
You mean straight line? Mm-hmm.
He's talking about lines.
Talking nonsense.
You're thinking of non-analytic stuff.
So this different time condition in the beginning, you needed to guarantee that there is one, at least
No,
one
degenerate.
the approximable point.
Yes, yes, yes,
Okay,
yes.
so somehow that's the only place where you.
Yes, yes.
Okay, any other questions? Okay, let's encourage.
And to
Are you thinking
double recording? Double recording?
lambda is